Okay. Um, okay, cool. So I think uh and design sessions. Yep, we can start now. So the screen content is being recorded. So this is the to-do question that we first want to start with, and then we can let me share my screen as well. So yeah, this is the to-do question. So let us put the date for today and start. So the first question we want to do, did anyone try out this question, the to-do one? Okay, sure. So let's go through that and see what we can do. Let's reset it to default. This is not exactly based on the two sum or four sum, three sum approaches that we had done earlier, but this is kind of looks like that, but a slight variation of it. So I would let you guys go through the question first, take a few minutes, go through the problem, and then I would like to hear your thoughts on it before we start discussing the approach. Let me know once you're done reading the problem and have understood it. I'm not seeing the Google Meet, so thumbs up might not be directly visible to me, so you can say if you have understood the question. Okay. And does someone wants to present his thoughts or her thoughts? What do you think? How can we approach it? So essentially, we are given four integer arrays, right? Four different set of arrays, and we need to find quadruplets, essentially an element from each one of these arrays, such that the sum of all these elements is equal to some specified number. Here, the number is already predefined as zero, but it can be something else also. Um, Remember that we had already done a question on the foursome where we were given one array, and we had to find out a quadruplet, which is four numbers from from one single array, such that it leads to a target sum. Right, that target sum can be zero or anything. Uh, but this, but in that question, the four numbers had to be found from the same array itself. Like we were given one single array from which we had to find those four numbers. But here the question changes. Here we are given four different arrays and we have to pick one number from each of these arrays such that the sum is equal to a given target sum, which is zero for in this case here. Um, so this question is a little different from there because in that problem, the way we had approached that the other two sum, three sum, and four sum, and even the generic k sum series is we wanted to break down the problem um, until it comes down to the two sum. So we will let's say if it's a four sum problem, we will first fix the ith element. then in a outer loop. Then we will fix the second element in the inner loop. Alex, yes. Okay. Would you like to share it? Mm-hmm. Mm-hmm. Hashes all the sums. And to what? To the indices that led to the sum. How would you, so you want to store both the indices like I and j. So essentially in your diction, so you are saying that we can take a dictionary. In the dictionary, the key is actually the sum, the potential possible combination of sums from nums 1 and nums 2. Let's say picking an element from nums 1 and then picking a second element from nums 2, storing their sum as a key, and the value is like the indices I and j. Probably you want to store these values in a list. Is that what you're suggesting? Mm-hmm. Okay. But what happens if there are more than one pairs in nums 1 and nums 2 which lead to the same sum? For example, let me here the elements can repeat also, right? We are not it's nowhere mentioned that the elements are distinct. So, and it also nowhere mentioned that we have to return the total So read the question. Most of the questions that we had done earlier, we had to return the unique tuplets or unique triplets or quadruplets. So, but here the question doesn't say anything like it has to be unique. Like for example, these are the small details about this problem, which so let's say that we are given the nums one. Let's just take two arrays for now. So it has 1 1 2 2. Okay, and then nums 2 has, for example, my 3 3 um 4 4. Okay, for example, let's keep them right now sorted, although question doesn't say that they are sorted, but right now let's just assume for the simplicity part. So if we are taking all the combinations, there are two different elements in nums 1, two different elements in nums 2. So in total, there can be four combinations, right? 2 multiplied by 2, total four unique combinations of the pairs. So one can be 1 comma 3, uh, picking 1 from nums 1 and 3 from the nums 2. So all possible combinations can be 1 3, then um, mhm. Store the count of indices. I didn't understand. So let's say you're storing the sum, right? So four is one sum. So if I use a dictionary, okay. So in the dictionary we can store the sum. That's definitely a good idea. Essentially this is towards the right approach. But let's say we store the sum. So the first sum is four. The second sum right now I'm leaving the value part empty. So this is a key value pair, okay? The second key will be 1 plus 4, 5. I'm leaving the value part empty here. The third key again is actually going to be 2 plus 3, okay? So, and the last sum is 2 plus 4, 6. So there are total three combinations, like three possible summation values. If you pick an element from nums 1 and pick an element from nums 2 and then add them up. So there are total uh, sum three possible sums that can you can get. in the value, what should we store? Mm-hmm. Okay. So let's say if we store the number of indices. So for example, 1 comma 3 is like one pair, right? So we initially stored 4 comma 1 here. Then we got 1 comma 4 as a second potential pair. So the sum is 5. So against 5 we stored its frequency. Basically we should be storing the frequencies. So I am storing 1 against 5. It means that number of times this sum has been seen or has been repeated is one time as of now. Then the next combination I have is 2 comma 3. But again, note that 1 comma 3 is repeated how many times? Two times. So it is going to be 1 comma 3 and 1 comma 3. Similarly, 1 comma 4 is again repeated. So all these numbers that I mentioned over here, they are repeated two times because 1 minute. Uh, so each 1, 3, yeah, they are repeated four times actually. Because there are 2 multiplied by 2 total 4 times, so there are two if you use a combination theory, so 2c1 multiplied by 2c1, so there are 2 times 1 coming, so you can choose one two ways, and then there are 2 times 3 is coming, so again you can choose a 3 two ways, so there can be total 4 combinations. Similarly, with every number, the way right now it is designed, we have two the twice frequency of each element that we notice over here. So there can be total 4 times. So I'm gonna update my sum as 4 times. So the first sum is 1 comma 3, which is 4. Then the second sum is 1 comma 4. 1 plus 4 is 5. Again it will be 4 times. So I'm gonna update 4. Then the next sum I get is 2 plus 3. This is again 4 times. So but notice that 2 plus 3 leads to the same sum as 5. So this number actually becomes 8 here. And then for the last sum, 2 plus 4, 6, this becomes 4. First of all, is this part clear for everyone? What we are doing and what we are actually storing in a dictionary? Okay. Mitasha, you also, is it clear? Okay, all right. But I want you to think about this. So let's say we have got, why are we doing it this way? First of all, I want you to think around it. And second, is there a better optimized approach than this? Same thing we are going to do for nums 3. So let's say nums 3 and nums 4 is also given to us. We are also going to find, so let me just write the approach. Step 1 is find all possible pairs from nums 1 and nums 2. So all possible pairs, you can do it in a worst case time complexity of n square, right? This is the time complexity that it will lead to. So you're gonna simply run two loops, one iterating over nums1, second loop iterating over nums2, and then you basically finding out all the possible pairs. Then the step two, and once you are doing that, you're gonna store their frequencies in the dictionary. So you're gonna save the sum and how many times that sum is seen in this. So you're gonna save it. Now in the nums two in the step two part, we're gonna do the same. Find all possible sum pairs from nums 3 and nums 4. But notice that what are we looking for right now? We are looking for the total sum to be 0, right? So essentially, this sum plus the sum that you will get from nums 3 and nums 4, the total sum should be 0. So essentially, we have already gotten the sum 1, and now we are getting the sum 2 from the step 2, which will be the sum of a pair chosen from nums 3 and nums 4. So ideally, we want to make both the sums equal to 0. That's the end purpose. So we are going to do the same. Um, we are going to do the same over here with respect to the nums 3 and nums 4. But when we do that, we're actually looking to find directly the total sum being 0. So we really don't have to first iterate and capture the sum in from nums 3 and nums 4 in a dictionary, like in a new dictionary, and then iterate it, and then iterate both the dictionaries and see like if they have the complementary sums or not. So is yes, correct. But now the question to you guys is, we can, so right now what we're gonna do is we're gonna pick a pair for each pair basically, for each pair from nums 3 and nums 4. We are going to find, we will check if sum is equal to uh, negative. So if the sum is equal to, let's say if the negative of this sum, or if the sum is equal to a negative of any value present in the original dictionary or not. So this is what we have to do. For example, if let's say I had two numbers here, -2 and or maybe -3 and -1. For example, let's say nums 3 contains this. Okay. Now, if you look at this, here we have -3 and -1 as one combination, and -2 and -2 as another combination, which leads to the total sum of -4. So what it essentially means is that I can pair up my existing pairs of 1 comma 3, and 1 comma 3 was leading to this total sum of 4. So there were four such pairs which were leading to the sum of 4. So if I use all those pairs which were leading to the sum of 4, and then find out all the pairs which are leading to the sum of -4 and multiply them together, we got our original answer, right? That's how it should be. But to multiply them, we need to first capture all the sums from nums 3 and nums 4 in a separate dictionary, then go through both the dictionaries, like iterate over both the dictionaries, and essentially like for each element in dictionary 1, then find the complement element like minus, here it is 4. Then in the other dictionary we can find -4, and then multiply both the frequencies together. That is one way, because total number of ways will be multiplication factor, not the addition factor. But there's a smart way of doing that. So multiplication means what? For each pair that I am choosing, let's say -3 and -1, let's say this is one pair that I found, right? Which has the complementary sum. How many ways are there to form, to complement it with the original dictionary and form a sum 0? How many, let's say if I choose here -3 and -1, so I'm doing the iteration. So I'm doing a double for loop over here, and I'm finding all the possible pairs from nums 3 and nums 4. So for each pair, let's say -3 and -1, how many ways, we can pair it with uh original, with the complement pairs from nums 1 and nums 2. So what should be this value? It should be 4, right? Because there were four values over here which were leading, four possible combinations leading to the sum of 4. So this can be paired with any of those four combinations, and it will still give me the total sum 0, because its sum is 0 and its sum is -4. So the, this is this is essentially what we're going to do. For each pair that we are going to find, we are just simply going to add the frequency that we had already seen in the dictionary. So the count or the result, we will just keep on incrementing with the, let's say, dictionary dot get um, whatever is the sum. So over here, whatever the sum that we get, let's say this is the sum 2. So whatever value we get from there, if let's say this value was not there in the dictionary, we will simply have 0. It means the complement does not exist. But if it is not there, but if it is there already, then we will find out what's the frequency of it that exists. And that's why we do a plus operation here. Is everyone does everyone understand why are we doing plus, and still how is it able to handle all the cases? Yes, result is what we are returning, but my question is not this. My question is everyone able to understand why are we doing plus here? And how are we still able to map all the combinations? Ideally, you should do a multiplication operation, right? So, for example, let's say there are four possible, let's say the sum 4 is occurring 4 times in the, and let's say in the dictionary 2, if I have minus 4 comma 2, for example, minus 5 comma 4, and minus 6 comma 5. So what should be the answer? Let's say if I had maintained these two dictionaries, dictionary 1 and dictionary 2, the answer would be simply multiplication and addition of these values, like 4 into 2, 8. So there can be 8 combinations with the sum 0. Then there can be 32 combinations with again sum 0. And there can be 20 combinations, 4 into 5, again with the sum 0. But since we are not doing this longer approach, we are not computing the dictionary 2 because that is like not really required. What are we instead doing is that for each pair, let's say here there are two such pairs which had the sum minus 4, right? So for each pair, we are adding the frequency 4 to it, like plus 4 plus 4. So it will become 8. So it is essentially the same. 4 multiplied by 2 is 8. And for each valid pair that we are finding in the nums 2, we are simply adding the frequency of the dictionary 1, which essentially leads to the same output. I just wanted to explain that because a lot of people just mug it up. They don't really understand like why are we just doing sum, and try to understand this question is specifically asking you to return all the tuples, so including the duplicate tuples. If the question had been only about let's say returning the unique tuples, then this approach will not work. We would have to tweak this approach. Is that making sense? One second. I had to I actually, someone asked me to add her in the meeting, but I forgot to send the link. Okay. Uh, okay. So basically, what's your question? Is it optimal, suboptimal to have two dictionaries? So in terms of the space complexity, nothing would change. In terms of the space complexity, you will still, is it given that all the, okay, so first of all, the dictionary one that you are choosing has a space complexity of m cross n, where m is the length of, uh, m is the size. One second, let me admit. Hey Palak, we are just about to finish this problem. This was a to-do question from the previous session. I'll be starting a new topic in next 10 minutes. So probably you can just stay and watch this, and then I'll be with a new topic in a bit, okay? Okay, so basically, Alex, the having a two dictionaries is definitely going to add up add up overall space complexity requirements. And the thing is that all these arrays can be of different lengths. It is nowhere mentioned that okay, it's mentioned that they are all less than n, I think, right? So, but there um I think it's mentioned their lengths are same actually. They have a same length here. So essentially the space complexity that we are using in this process is big of n square. But if we were to use two dictionaries, the total space we would be end up using is twice of big of n square. So this doesn't change in terms of the big O notation, because uh, 2 is simply a constant. We can ignore it and it is still going to be n square space complexity. So so this can be the space complexity in terms of big O notation doesn't change, but yes, this does change a little bit things. Especially you need to first iterate over the second array, and create this dictionary. Then after that, we need to iterate over one of the dictionaries and then keep finding the complement pair in the second dictionary. So there is one added operation that needs to be done, and second, there is one extra dictionary that we need to initialize and store the results. So in term like ideally speaking, in terms of space and time, nothing changes, but yes, one extra iteration and one additional hash map we need to create. Sometimes interviewers can be little because most of the interviewers they have the solutions in front of them, except let's say if you're sitting in a Google interview, Google interviewers mostly come out with their own questionnaire set, so they don't have like those questions are not readily available online. But let's say if you're sitting in an interview with Meta or Amazon, most of the questions they just blindly ask like LC medium problems or uh, LC hard also. I recently saw like Facebook asking about alien dictionary, which is a topological sorting DFS problem. But anyways, so all I'm saying is most of the times they have the solutions in front of them and they're looking for the most optimized solutions. So so make sure that try to reduce the number of operations and try to consume as less of a space as possible at at all times. Does that make sense? Okay, so we can implement it. Let me just comment everything over here and um we can implement this. So essentially what I'm gonna take is uh I'm gonna take a dictionary. This dictionary is going to store the sum for nums 1 and 2. So then I'm going to iterate over the both the nums 1 and nums 2. So I can just say like this, num1 nums1 for int num2 nums2, and then we can say so we are finding out all the possible pairs from the first and second array here. Then we compute the sum num1 plus num2. Then we can check and we can insert this sum inside this hash map. So map dot put sum comma map dot get or default sum comma 0 plus 1. So this is simply a frequency map for the sum. So initially the frequency map will be initialized with 1 if the sum is not there, and otherwise we find the existing frequency and we increment it by 1. Once we are done with this, now we have iterated over the first and second array and created this dictionary. Now we can initialize a result, and then we can iterate over the in the similar fashion. I'm just gonna copy it. So we can iterate over nums3 and nums4. So num3, nums3, nums4, num4. Um, okay, so we can get the sum first of all. This now what we are looking for, we are not trying to put inside the map now. We are looking for a sum, the complement of the sum if this exists. So what we are gonna say, if map dot contains key minus of sum. Basically, we are looking for a negative sum, right? Inside the map. If it exists, it means that we have found a tuple or with the four numbers such that their sum is equal to 0. This exactly means that. So what I'm going to do is, in this case, I'm just simply going to append the frequency that I had already stored from nums1 and nums2. It means for this pair that I have found so far, uh, total how many combinations can be created, which is the original frequency found in the map. So map dot get minus sum. Okay. Otherwise, otherwise we don't need to do anything. So if this is the case, then we have gotten the result, added to the result over here, and at the end we can just simply return the result. Does that make sense? So let's try to run this and see. Okay, this passes. Let's submit it. Okay, so what's the total time complexity for this overall algorithm that we have done? Yes, and space is also n square. So if we write it, time is big of n square and space is also big of n square. So let me just copy this code into our doc. And let's move with the So I hope this question is clear to everyone. So let's start our next topic for today. So the fresh topic we're gonna start for at least 1 to 2 weeks is going to be binary search. Yes, Mitasha. Yeah. Yeah. So okay, so first of all, what I have seen in my findings is that this runtime and memory depends a lot on the let's say which language you're using first of all, and second, it's not a constant thing. So let's say if you run it, the runtime is pretty constant, but then the memory keeps changing every time you run it. It's not consistent. So and in terms of the time complexity, like I feel this is like the best this is the best optimized solution that you can have for this particular problem. Probably if you run it in a different there can be few generally when folks there are two things when it comes to the programming. One is called a competitive programming, and second is called the programming with respect to your fang interviews. Both are different. Competitive programming means that you want to make your code run as fast as possible from all the contestants, and most of the platforms where you practice your competitive coding is CodeChef, Codeforces. LeetCode is not actually the platform for that, just to say. And in those cases it matters like how much exact memory your code is consuming, and those platforms are pretty accurate in terms of that. But on lead code, what matters is if you are using the most optimized solution to solve the problem, if you are able to understand all the edge cases, all the corner cases, if you are able to dry run your code for any sample input, and you can explain like for each iteration how the code is behaving. That is what is expected, and that is the purpose of it. So I would say that do not really focus on this. Uh, you can probably like shorten this up, and maybe if I don't use two for loops, do it in a lambda. Let's say Java has lambda operations, right? So if I do that, it probably might run faster. And I can probably use a little bit of a hacky code to make it run faster and beat this. But there is no definitive advantage here. If you really want to do that, then do it in Code Forces or Code Chef. There are weekly contests, there are long challenges, long running challenges that keep on happening over there. So you participate over there and do those. But here it's not really a matter of concern. So yep. Does that make sense? Okay, all right. So next thing that we want to start is the binary search. So let's start with the questions itself, and we'll explain it with respect to the questions. So maybe the first, we had a set of questions that we wanted to do in the binary search. So the first question for the day that we want to start with is searching. This is the problem statement we want to do. Search in a sorted, rotated, and sorted array. Uh, would you guys also like me to solve the very basic question searching in a sorted array? I hope that everyone knows about, right? Or would you like me to also cover that? Okay. And what about other folks, Mitasha, Palak, both Palaks? Sure. All right. Let's do one thing. Let's do it. So what does binary search means? Binary search basically means that you are the purpose of binary search and what it actually means is that you are reducing your search radius by half every time. This is called binary search. So especially even in your production code, right? Sometimes let's say something breaks generally, and you have no idea from what iteration or from what let's say last PR it was breaking. So a lot of times people do kind of a binary search over there as well. So let's say today the code is breaking, today the build is breaking, and the last fixable build was 1 month back, for example. Now you want to find out which exact point the build started breaking. One way is to go through each and every build, deploy it in your machine, and then test it out, like from where it started failing. The second way can be a binary search. So you essentially go to the middle point. So essentially what you're saying is that you have a linear array. First of all, binary search works on the linear kind of data structures, or where you have some sort of ordering with respect to your data structure. So it works on linear data structures, and then works on ordered data structures. So ordering means that the element should be ordered in some manner. It can be ascending order, descending order, or you can call it non-increasing and non-decreasing. We highlighted couple of differences last time. What's the difference between a ascending order and a non-decreasing order? Essentially, they might sound same, but not exactly. So non-decreasing can contain duplicates, whereas increasing is like strictly increasing. So there is no duplicates in the increasing. Similarly, decreasing and non-increasing you can decipher it accordingly. But binary search works on linear data structures and it works on the ordered data structure. The idea is that we want to reduce the search radius by half every time. So currently every single iteration we are reducing the length. You can say the search length or the search. I wrote it as a search radius as a generic thing. So in every single iteration we're reducing the search uh the length or the size of the array by half, or size of data structure by half. Now we are not exactly reducing it by half practically. We are reducing the search um, the searchable or the search radius basically. That's what we are reducing. Okay. So just to give an example, if we have an array like this where 1 4 5 6 7 8. Now if someone asks you to find out if number, let's say target 6 exist inside this array or not. One way is to just do a linear search in this array, going step by step, and then iterate over the complete array. But is there a better way to do that? There's a better way to do that. Since we know that array is already sorted, it's a sorted array and it's a linear data structure. So both of the conditions are being satisfied, which we wrote in the line number 1 and 2. It's a ordered and it's a linear data structure. So we can simply apply our binary search. Also, one more thing before going there, you should be able to uh, jump to the middle element, or let's say the you should be able to jump to any element, let me just write it as like this: any element or the middle element in big of one time. This approach doesn't specifically work on the linked list, because in linked list there is no way to go to the middle element in the big of one time. You have to actually iterate to the middle element, like one step at a time. But in arrays, since arrays are, as we know, arrays versus linked list, arrays are stored in contiguous memory locations. So your compiler and your operating system basically, the way the array is initiated and initialized, all of these elements are stored in the contiguous blocks. So if you need to go to the element number 5, it what your Java, or let's say what your Python interpreter will do is, it will simply it only stores the first index, the memory address of the first location of your array, and then it will add an offset to where you want to jump. So here the offset is 2, 2 multiplied by the length of the size of your data type. So let's say the size of array is 4 bytes. So it is going to jump 8 bytes ahead from the first memory location, or from the 0th index memory location. So that's why it is pretty fast. Like, it doesn't really has to iterate over 4 to go to 5. It can directly jump to 5. Um, Okay, so coming back to the binary search part, we the generally what we do is we say that, okay, we want to search in the entire, the currently the search radius is this entire array that we have. So we have two pointers, L left pointer and right pointer, where we mark as the so this can be array dot length -1, for example. So these are the markers that we have for the search radius. And then at every iteration, we want to reduce the search radius by half. This is the very first thing that we wrote in the binary search, right? So maybe let me write it as a point instead of. So at every single step, we should be able to uh, we are reducing the search radius by half every time. So what we're gonna do over here is we'll be choosing a mid point. Mid can be L plus R by 2. Generally, when we are doing L plus R by 2, it is this is like the midpoint, right? So starting from L and then R is the ending point. But generally, it is advisable to write it in this manner: L plus R minus L by 2, instead of writing it as L plus R by 2. Why is that? Because to avoid the overflow. So it can happen that your array is pretty big, and it is this problem may not come in Python. So if you're working on a Python language, Python since Python is not a strongly typed language, it does not define the data types. So it automatically, I think, assumes and creates the highest data type, not specifically like a int range, and its range is pretty high in Python. But yeah, if you're working on a language like C++ or Java, then you should use this notation L plus R minus L by 2 to avoid the overflow. Overflow can happen if L plus R let's say if R is pretty huge and L is also, so if L and R are pointing to, let's say, the second last and last index of the array. Let's say we are in this iteration and it happens to be the case where L is pointing to the second last index and R is pointing to the last index. So the summation of these two values can overflow your integer and your data type range that you are choosing. So that's why, but doing it in this manner, L plus R minus L by 2, effect is exactly the same. This is also going to give you L plus R by 2 itself. So if you expand it, this will become like L plus R by 2 minus L by 2. So this is nothing but same as L by 2 plus R by 2, which is like L plus R by 2, correct? So this is same as the first notation that we wrote over here, but this avoids the overflow. So anyways, so first you get your middle value or the middle element, then you compare, then you do the comparison with respect to the middle. So if you're searching for a target 6, you do make a comparison with the array mid. So here the mid will be like, for example, here we are having the elements as 0, 1, 2, 3, 4, 5. So the middle will be 2. So since we are looking for a target 6 and the middle is 2, So it means that the element does not exist in the middle, can only exist in the right side of the array. It cannot exist in the left side of the array. The reason is that it is a sorted array and the target that we are looking for is greater than the middle. So what we're going to do is in the next iteration, we are going to shift our L to m plus 1 and R will remain the same. So the next time, now the search radius has become half, and now we are searching in the half of the array, like in the other half of the array, 6 7 8. We ignore 1 4 and 5 completely, so we only search in 6 7 8. So L becomes 3, R becomes 5, and then the mid becomes 3 plus 5 by 2, which is 4. So we check it with 4. Now we notice that, oh, it is less than, target is less than the middle. So go one step back. Then we go one step back. L and R both point here itself. L is also pointing to this and R is also pointing to this. Then we again do L plus R by 2. And then we check the middle value. Like this is the mid is same as 3. And then we compare it and we get the answer and return. If let's say the element does not exist, the conditions will terminate and we will not be able to find this value. Um, does this help to refresh things, or do we need to also like go through into the code for it, like the basic binary search code? Okay, so can we go to the problems, like the problems that have been asked in FANG, and which are the most favorite questions related to this topic? Okay, so the very first question related to this topic is searching in a sorted and a rotated array. So basically in this problem, what we are given is, read this problem clearly, that the integer array is there which is sorted in the ascending order. Ascending means like there is a distinct elements. Here it's mentioned distinct, but it automatically means it's a distinct elements. It's completely ascending. If it was not distinct and if it was duplicate, then it would have said like non-decreasing order. Okay. Um, so that's the very first point. Now after that, possibly, so here the question says that the array that is given to us has been rotated at a given pivot index. So for example, this is the array 0 1 2 3 4 5 6 7. It has been rotated at some point. So when you rotate it, like so all the right hand side values will come to the left. So you can rotate it from any point. So for example, if you rotate it at index 0 1 2 3, at index here, like 3 here, so 4 5 6 7 will come in the front. So this array will become like this: 4 5 6 7 0 1 2. So essentially what does the rotation means is, the array is the same array, but uh, all the right hand side, like some set of right hand side values have been shifted to the left. That's what the rotation simply means. So any part of your right hand side values have been shifted to the left. Is that part clear? What does the question talks about? And what we need to find out is, we need to find out if a given target, if a given number exists inside this array that we are, the rotated array is given to us. So we'll be given this rotated array. All the elements are unique inside this. There is no repetition here. And we need to find out, in case, if the target exists, then we should be able to return the index of that target position. Like for example, here we need to search the target 0. 0 is present where? 0 1 2 3 4. It is present at fourth index. So we should be returning 4 here. Okay. If we are searching for target equal to 3, then 3 is not present. So we return -1 in this case. So essentially the question is like we should be searching for any target. So using a binary search model. And also I think in the coding doc, I just forgot to mention that binary search runs in log of n time. So the why the binary search is preferred is it runs in big of log of n time. Um, do you guys understand like the logic of log of n? Why is it log of n and why not something else? Uh, you must have studied this in the college. No, if it is linear, then it will be big of n, right? So every time you're reducing it by 2, by dividing it by 2. So just to give you an example, if you have n, so what I'm doing is every time I'm dividing n by 2, then further I'm dividing the n by 4. It will then further it is going to become n by 8. So basically what we are looking to find is we are looking to every time we are multiply dividing it with the higher multiplication powers of 2, right? So 2 raised to per k, we are looking for k such that just to generalize this theme, we are looking to find the value of k such that this entire thing will become 0, for example. So this entire number that we are searching for becomes 0. This is what we are looking for. So, or I think like you want to reduce it to the bare minimum. So if you, I think it should be 1, not 0. So if you convert it with respect to the n divided by 2 raised to per k should be 1. So n should be equal to 2 raised to per k. This is what you are searching for. So the value of the k in this process is nothing but log to the base 2 log to n, where 2 is the base. So this is like a standard mathematical notation. So that's why uh, and k is what? K is the number of steps or number of iterations you're doing. So in the first iteration, it will become 2 raised to per 1. In the second iteration, it becomes 2 raised to per 2. Then in the third iteration, it becomes 2 raised to per 3. Like the size becomes 2 raised to per 3. Okay, so how many iterations you are doing basically? So 3 iterations you did here, and here you did k iterations to reach to the desired output. So that's why, and if you compute k using the reverse, using this mathematical operation, it will become log of n. Does that make sense? Okay, all right. So coming back to the question, a search in a rotated and rotated sorted array. So over here, we are going to use the binary search model, and this is going to be the first set of code that we'll be writing. But before that, any thoughts? Like, what do you guys think? How we can solve this question? There are a couple of ways to do it, but I want to hear if someone has already done it before and if they recall few things. Okay, okay. Mm-hmm. Um, kind of, but the explanation is not proper. Like, why is that? Why is the reason? Uh, so essentially, let's say we are taking this array, okay, nums array. So what's the approach, right? So we will find a middle element, right? Using this operation. So definitely we have to find the middle. So this is L, and let's say the R is starting here. So I'm just gonna right now discuss a generic approach, and then we'll discuss couple of other approaches as well. So the first way that you can solve this problem is first you can find the like the pivot element from where the array has been rotated. So here the pivot element, or basically you can find out the minimum element of the array. So minimum element is 0, right? And then you know that the right side of the array is sorted, and then the left side of the array is also sorted. So then you can check if your element is lying in this array, then you can do a binary search in this part. That's one operation. Or if your target lies in this part, then you can do a binary search in this, and that's pretty easy to find once you have gotten the minimum element, But for that to happen, you need to use two binary searches, one to find the part or the middle element or the minimum element of this array, and then the second operation you need to do is to actually search, is to do a second binary search to find the position in the appropriate part of the array. So like for example, if we had to search for 5, right? So first we will find out where is the minimum element of this array, which is a pivot, and then we know that and then we will check if 5 is lying in a range, which is pretty easy to check in a single if condition, right? If 5 is in between 0 and 2, then you mean you can do a binary search in this part. But in this case, the 5 lies in the first half. So it means you can do a binary search in this part, which is, so you can fix R onto 7, L onto 4, and then do a binary search here, and then find your respective target. That is like one way. Does everyone understand, like, this could be a desired approach? But here we are using two binary searches, one to find the minimum element, and you should know how to find a minimum element, by the way. We'll do a separate problem on it altogether, so I'm not going to discuss it in this question, because there is a there's a next problem that we're gonna do on this. So right now we are gonna discuss an optimized approach where we will just do it in a single binary search. The approach says that first, definitely we are going to find out the middle element, right? So find the middle. That's the very first part. In fact, let me do it in Python this time. So the first question we did in Java, so this one, let's switch to Python. Okay, so um, okay, so over here, what we want to do is first we want to find the middle element. So we start from L from 0 and R from the end. So we mark our mark our pointers L and R. Okay. Then find the middle. Once we have found the middle, we will check which part of the array is a sorted range. Since this will be very easy to check, the reason is that this array is like contains all the unique elements. There is no duplicates. Please remember that part. If the array contains the duplicate elements, then this approach doesn't work and it has to be tweaked. Uh, so so now basically we'll find a middle element. So let's say the middle element comes out to be let me name these numbers as 0, 1, 2, 3, 4. So these are the indices 5 and 6. Okay, so L starts from 0, R starts from 6, and the M, the middle element, is going to be L plus R by 2, which is 3. Now once we have gotten to the middle element, let's say we were searching for value 1. Okay, so for example the target is 1, we need to find for 1. Now we are going to check whether this middle element that we have, we will check it with respect to the rightmost element. Why are we going to do that? This way we will, or you can check it with respect to the leftmost element as well. Any boundary you can pick according to your own choice. So let's say if you are searching this middle element with respect to the rightmost element, in case if this middle element is greater than the rightmost element, it means that, what does it essentially mean? That it actually means that the left part of the array is sorted, and then the right part of the array is not. uh, like the left part of the array is completely sorted, but the right part of the array is not completely sorted. There can be there can be a pivot element sitting over there, so the rotation might have been in that place. Using this, you're going to decide whether to go left or to go right. For example, we checked 7 with respect to the rightmost element 2. We know that 7 is greater than 2. It means that the sorted part is only the left side of the array. This is the very first part. So using the middle, uh, what we're going to do is find the sorted half. Find the sorted half, either left left side or right side, depending upon using using the comparison of middle element with right rightmost or leftmost marker. Okay, leftmost pointer. So basically, this is the very first step we do. Once we have gotten the sorted half, right? So now we know that in the sorted half, we can easily find whether this element lies in the sorted half or not. If it does not lie in the sorted half, we can actually ignore the sorted half and go to the and then just start processing the other half. So in this case, I know that my left hand side is the sorted half, right? So 4, 5, 6, 7 is the sorted half. I'm going to compare if my target is going to lie within this. So essentially what I'm going to compare is if target lies in this between 4 and 7. So if target is greater than or equal to L and less than equal to M, but that's not the case. Target is actually less than M. It means that the target lies in the second half. So I can just simply shift my left pointer to M plus 1. So left will simply go to uh, m plus 1, which is 4 here, and the right will stay to 6. And then the same operation we will be doing. And at every point we are doing it, we are finding the middle and comparing the middle with the target. That's the very first part that we do. And then we go to this comparison logic. Does that make sense? Uh, does this make sense to everyone? Palak? Okay. So we'll do a dry run, don't worry. Let's first write the code and then we'll do a sample dry run as well for this. In fact, let us do the dry run first and then write the code. Okay, so let's say that we had to maybe I just increment one more number here, 3 also. Gonna put its index is 7 and we are searching for 2, for example. Now 2 lies in this part of the array, right? So initially L is 0, R is 7, and the midpoint is 3. This is the very first iteration. So in this iteration we check. So for the iteration part I'm doing a tab to make sure that like this operation is happening within this iteration. So maybe you can write it as a #1. This is the first iteration. Inside this, what we do is we check if array of mid, let's say array of mid, which is 3, is if it is less than my array of right or array of R basically. If this is the case, uh, since we are using nums, so I'm just going to use nums notation here. If this is the case, then in that case, I know that my right side of the range is sorted. So if this is true, it means my right side range is sorted. But is this the case here? Let's check it. So nums of mid is 3, which is 7. 7 is 7 less than the rightmost element 3? No. So it means my right side range is not sorted. Then I will go to the else part. In the else, it means my left side range is sorted. So I'm going to compare it in my, so we are going to compare the target using the sorted range, like which range is sorted. Then we're going to check if this target is lying in the sorted range or not. If it is lying in the sorted range, we will just switch to that sorted range and start iterating and start doing binary search on that range. But if it is not lying in that sorted range, it means it is present in the second range, which is the unsorted range. So we shift to that the second range and start doing binary search on that. Simply, this is like the algorithm that we are doing. So I'm gonna write the code, but let me know if someone is not clear on this approach that we discussed. I can explain it further, but for now, I'm just gonna write the code. So here I'm gonna define my L, which is 0, R as length of my nums minus 1. Let me comment out the below portion that we wrote. Okay. Now I'm gonna define, I have defined my already L and R. So we are simply going to, uh, switch to the while loop. So while L is less than equal to R, now we will be first finding out the mid. Mid is going to be L plus R minus L by 2. Once we have found the middle element, now we are going to check whether which half is sorted. Is my, let's say, second half is sorted. So I'm going to check this. So if array of m, nums of m, is less than nums of r. So if it is less than, let's say if it is just one element, so I'm just going to use a equal operator. If it is less than equal to this, it means it's a sorted, this is a sorted range. So I can compare if my element lies in this or not. So that's what we're gonna do if it lies between this or not. But before doing it, we have found the middle element, so we can first directly check if the target is same as, if the target is same as the middle element, then we just simply return, then return the, since we have to return the index, we don't have to return the target itself. So I'm gonna return m over here. The second thing I'm gonna check is if my second half, if my right side is sorted, is my right side sorted. You can do it reverse way also. You can check for the left side as well, but I'm just doing it for the right side first. So I'm gonna check if this is sorted. Then um, I'm going to check if the target lies in this range. So if target is greater than equal to nums of m, and target, it cannot be equal to nums of m because already we have checked for equality part here. If it was equal, we would have returned it here itself. Or if target is less than equal to nums of r, if this is the case, then it means that we have to go to this right range, right? It means the answer, the target should be lying in the right side range. So I should be shifting my L to m plus 1. That's it. Else, otherwise, if the target was not in the right side range, definitely it is in the left side range. So I can just simply shift my R to m minus 1. Uh, this is the part if my right side range is sorted. If my right side range is not sorted, it means my left side range is sorted. So I'm gonna write over here the else part. One second. So else, so this means my left side sorted. Okay. In the else part, we are going to check if target is going to be is like greater than the nums of L, and it is smaller than the nums of M. So if target is greater than equal to nums of L and target is lesser than nums of M. So it means that the target is actually present. So left side range is sorted. That's why I am making this check. So please understand why we are making this check here, because we know that the left side range is sorted, so I'm allowed to make this check. In the line number 11, we checked that we came to the conclusion that if the right side is sorted, then we are allowed to make this check. Okay, we are not, so we are first checking which side is sorted, and then we are making the equality checks to decide in which part the target is lying. So in this case, if the left side range is sorted and the target is actually in the left hand side, so I'm just simply going to do r is equal to m minus 1, else um, l is equal to m plus 1. Is this part clear what we are doing over here? Okay. And then finally, let's say in case if the target is if target is found, then we would definitely return it over here, return M. But if the target is not found, then we will not be able to return it. Like, so in that case, we will simply say um, return -1. So because -1 is what we need to return if we have not found the target. L- Any doubts in this? Let's try to run it. But any questions so far? Indices must be integer and not float. Okay. So L plus R. Yeah, I think Python has this thing that by default it takes we need to specify it as an integer. 1 second. //2. Okay. Like this. All right. Yep. So let's try to submit it and see. Okay, so any questions, any doubts in this so far? And whenever this question comes to you during the interview, please do this way itself. I mean, you can tweak it instead of checking for the right side sorted first, you can check for the left side being sorted first. But please do not do two binary searches. I have seen this happening a lot, like especially even when I was in the interview panel also, I would also, if someone just solves it using the finding the pivot first and then doing the second binary search to do, I would ask them to do it in a single search because that's what the expected guidelines are for us, for interviewers. But what I'm saying is, please do the most optimized version. So this is using a single binary search, and the time complexity for this in the worst case is going to be log of n. So worst case time complexity is log of n even for in the worst case. Does that make sense? Okay, let me just copy paste this in the doc for the reference. Uh, and the problem that we did today is this first problem. I mean, the second problem of the day. So 1 second, boss. Heading to. Okay, so find number in the sorted array. Cool. The okay, the next question that we want to do today after this is the part two of this problem. In fact, before doing the part two, let's do the pivot problem, and then we'll do the part two of both the questions, which are the uh, hard problems. Okay, sure, Palak. Um, Okay, by the way, did you guys also do the previous question in your own lead code ID? I want each one of you to implement that the same in your at your own end. What we did here. Have you done it as well on your lead code? Maybe take couple of minutes if it's not still done. Meanwhile, Palak is back. Alex, did you do it? Okay, and Mitasha and Palak one. Palak, sorry, I'm just calling you Palak one and Palak two just to distinguish. S- Mitasha, are you done with this question? Okay, all right. So let's jump to the second problem, which is finding the minimum in a rotated and sorted array. This essentially is like finding the pivot, which we were talking about, right? So here we need to find the pivot, and please note that it contains only unique elements. There is no repetition of elements inside this sorted and rotated array. After doing this, we'll do the variations of both the problems in which the elements can get duplicated, and those are a little tricky to handle, but we'll look after this. So let's start this problem. Basically, here we need to find the minimum element. We are not looking to find the we just need to find the pivot or the minimum element in the sorted array. So what do you think can be the approach to find the minimum element? We can find the place where it is less than the previous element. But what happens in case if there was no previous element? Let's say if so imagine, let's say if I give you the array like this, which is not rotated. So it's not necessary that element has to be the array has to be rotated. There will be some edge cases where I just give you array like this. Then there is no previous element to this. Yeah. Or can't it be like this? Let's say if I find a scenario where my left is, let's say this is my left, this is my right. I know that all are um, essentially all elements that I have in this array are unique elements. So if my left is less than R, for example, because I know that left is fixing the radius, the search radius. So and the right is fixing the other side of the search radius. So if my left is less than R, then I know that whatever is at left is the minimum. Like for example, if I take the other example, which actually has the rotation. So if I, while doing the binary search, if we happen to come to this, let's say L comes here, R comes here, then L is actually less than R, right? So it means we have gotten the minimum element, right? The other approach can also work, which you just mentioned, Alex. So if uh, the other approach that you mentioned is if array of, let's say I is less than array of I minus 1, or just to handle the edge case, you can say if I is equal to 0. There is no, if I is equal to 0, and if I is equal to 0 or array of I is less than array of I minus 1, like this, if you are able to reach to this particular index while doing the binary search, then we can say that, yeah, we have found the answer. Essentially, what you're saying is array of mid and mid minus 1, right? If I'm able to understand you, right? This is what you're intending to do. Definitely, we can use this also. Let's first try to implement it according to the way that I am saying, and then we can also discuss this the second way of doing things also, in which we can simply compare it with the previous element. So over here, I'm gonna start with L is equal to 0. Uh, R is equal to length of nums minus 1. Then I have my loop L is less than R. And then inside this, we're first gonna find L plus R minus L divide by 2. Uh, okay, so once we have gotten to this, now we are going to check if first we can check actually if my nums of L, the approach that I'm talking about is if nums of L is equal to less than equal to nums of R, it means that we have found the pivot. It means we have found the minimum element. So L is the minimum element in that case, and we need to return the minimum element. So return nums of L. Then we can find the middle element of it. And now after finding the middle element, now we can we can compare it. Um, okay, so now we can check like if which part of my array is sorted. Since I know that the minimum element is always going to be in the unsorted territory. Why do I mean by that is, like for example, let's say if my array is like this, 0, so I find a middle element which can be, let's say, 1 happens to be, or it can happen to be 7. So if I look at the left side, which is the sorted range, and the right side is the unsorted range. So wherever the pivoting happens, the minimum element is always going to be in that range, which is going to be the unsorted part of the equation. You can take, for example, in any other example, maybe mm, let's say the it was instead of it was like this: 1, 2, 4, 5, 6, 7. Now if we look at the unsorted part of the range, let's say 1 is the middle element, so we compare it with the right side, the rightmost r, and we come to the conclusion that so L starts from here, r starts from here. Then we come to the middle element. Let's say the middle element is pointing to 1. um, we need to see if it is actually pointing to 1 or somewhere else. Maybe we can just do that: 0, 1, 2, 3, 4, 5, 6. So yeah, the middle element is pointing to 1. So we compare it with 5, which is our rightmost index, and we check if the value is actually strictly less than or equal to r. It means we have a sorted right part. Now we know that for a fact. We actually don't need to check it whether 0, because we don't know what's the minimum element we are searching for, right? But we can for sure safely say that minimum element is not going to be present in the sorted half. It is always going to be present in my unsorted half, because unsorted half is where the rotation happened, and that's why it became unsorted. Is that making sense? Let's take that: 6, 7, 1, 2, 4, 5. So the middle element will be this is L. So 6 is the middle element is comes out to be 2, correct? Middle element comes out to be 2. So this is my middle element, right? So basically the minimum element is the middle element. Fine. But what we are saying what we are saying over here is we don't want to go to the right part of the array, right? We don't want to go to the right part of the array. We want to go to the left part of the array. Definitely we have to include the index m where m is being there, but this is the range that where we want to go to, which is the unsorted half. So the r will be set to m, L will be set to 6, and then again we're going to do the same process. So we'll find m over here, and every time we are checking if L is less than R, it means L is the minimum. Here again, L is not less than R, so 6 is not the minimum. So we find M, okay. Then we compare it with R. We check if is this the sorted range. This actually turns out to be the unsorted range because M is less than R. It should have been M is greater than R here. Otherwise, it should have been less than R if it was a sorted range. So it means we have to go to the sorted range, which is the right side of it. And since this is less than since M is greater than R, so the way the L and R will be designed, L will be pointing to M plus 1 in the next iteration. So what it means is L and R happens to point at the same 1 for the next iteration. And now the condition that we have in line number 6, if nums of L is less than equal to nums of R is satisfied, then we return that element. So 1 is returned. Does it make sense? So over here, as I said, we are looking to find out, the idea is that minimum element always lies in unsorted half. So find if right side is sorted. To do that, what I am what I'm going to do is, if right side is the sorted one, so basically we can actually find out if it is an unsorted one. Okay, so I mean we can do it in either way, but since we are looking to find the unsorted half, right? So essentially we can just check for the unsorted directly. So what we can say is, if nums of m, when will it become unsorted? Can someone tell me? If I have to compare it with the right, when will it become unsorted? Definitely, awesome. So if nums is greater than my right, then it becomes the unsorted half. So if this is if this is the case, it means I have to search in the unsorted half. So L should become m plus 1. Else, now it means that my left part is the unsorted half and my minimum should be there. So my right should become m. And now notice that here I'm not doing m minus 1 for this particular edge case. The reason is that in this case my nums of m is actually less than equal to r. It means that my left side is the unsorted half. It can possibly happen that the middle element itself is the minimum element that we have gotten. The case that right now that Mitasha was asking, right? So in this case, we happen to find the middle at this was the one. Initially, when we got to the middle, this was the middle element. So we first checked if it is a sorted, if it's an unsorted half, it's not an unsorted half because the middle element is strictly less than the right side element. Now we know that it is actually less than the right side element. It can possibly happen that this might be the minimum element itself. So what we're going to do is, when we switch to the left side, we don't want to ignore this element. This is the point that I spoke about when we were doing this test case. So we don't want to ignore this element, and I want to put my right pointer, the right side boundary to here, and then the left should point to here, and then search in this part of the array. This is what we are doing. So I shift my R to M and L stays where it was by default. Does this make sense? After this, we come out of all the while loops and we simply return. Like if we have found okay, here is one thing. If we have found like the minimum should get returned in this operation itself. So we should be able to return the minimum while doing this. So we can just return L just for the sake of doing it, but we should be able to find the minimum while as part of this iteration. But here we needed to return something because to complete to complete this function, it should have a return type. So here it's a conditional return, but yeah, so we have to return something. So I'm just returning L here. But the code should actually be running inside for the line number 6. So some issue is happening, runtime error in line number 21. Okay, sorry. We need to comment this part. Okay, so this passes. Let's submit it. Okay, we're getting a wrong answer. Let's check it out. What's why is it happening? Output is 0, expected. Okay, sorry, I'm returning L. Instead of that, it should be nums of L. but we need to check why is it going there. Yeah. So why is it going there is because there's a single element inside our array, which is so L and R are both pointing to the same. In fact, if I make this condition equality condition, I think it should pass. So maybe first let's try to submit it and then we can. Okay, so this passes. Um, I think Python runs better than Java, I feel, in terms of if I write the same code in Java, it will not beat 100%. I'm sure about it. Um, yeah, like, is this part understood? We were returning this for the single element. Let's say if the array contains just one element, so the test case that we were having the issue was in case if the array has a single element, then it will not go inside the while loop. So maybe if I just do a L less than equal to R over here, only problem with that is we need to be little careful when we are doing the assignment R is equal to M. We need to check for a scenario if it may not turn into an indefinite loop. So if you look very carefully the previous question that we were doing, let me just share my screen. So on that particular question, so in the binary search you have to be careful about one small thing. This L less than equal to R or less than R, whichever you want to do, you just want to be make sure that you don't stuck in an indefinite loop. In what cases you can stuck in an indefinite loop and in what cases you will not be stuck in an indefinite loop. If you're always incrementing and you're assigning your left and right pointer as +1 or -1, it means you are actually moving away from the current middle element that you're like right now looking at. Um, so in all these cases, it is completely 100% sure that you will not be running into an indefinite loop thing. So you can, even if you can straight away use L less than equal to R. But in the cases where you are actually equating it to M, there might be a scenario. I'm not saying that there will be. You need to do a little bit of a back testing on a smaller input array to check that if you do not run into an indefinite loop. Like for example, let's talk about the scenario in which this else condition will be true. This else condition will be true if minimum element lies in the left side, right? So this else condition will be true if the minimum element lies in the left part of it. So maybe if I take an example, like these are the things that I had faced when I was solving these questions. So let's say if you sometimes you will I most of the times use less than equal to operator, um, so as to cover all the scenarios. But then you need to be little careful with respect to running the indefinite loop. So like for example, if I take this 2, 1, 3, 4, is this a valid example? Uh, Not really, right? So it should be 3, 4, 1, 2. This can be a valid example. 3, 4, 1, 2. Here the 0, 1. But here we will not go into the right side. So we need to go into the right side. So we go in, like we need to go into the left side basically. So the minimum element should be there on the left side. So if I remove 4 from here, then yes. So if I remove 4 from here, then we will be going into the left side. So the middle is 1. So if I do a dry run on this, let's do a dry run on this, okay? How does a dry run looks like? If interval asks you to do a dry run, so you initially take L0, RS2. So you just assign the indices to these. So it becomes 0, 1, 2. Then you find the middle. Before finding the middle, you first check if nums L is less than equal to nums R, which is not true. So 3 is not less than 2. So it means this is not the answer. So now you find the middle. Middle will be 1. 0 plus 2 by, so it will be 1. Now you're going to check if your right side range is the unsorted range. Since your middle element is not greater than the the right the right element. So it's not an unsorted range. It means we have to go to the left. So to go to the left, in the next iteration, what do we do is the left remains unchanged, but the right becomes 1. So the right changes to mid that we have over here. Now we compare L and R again. Is L smaller than R? Not really. So it means this is still not the answer. I'm still going to find the middle. Now middle element 0 plus 1 by 2 is 0. Now at this point of time, I'm going to check if my right side range is unsorted. And actually the right side range is unsorted because my nums of m, which is nums of 0, is greater than nums of r, which is r is equal to 1. So, and the value itself is 1 over there. So it means I go to the right side, and in the next iteration, my L becomes m plus 1. So L becomes 1, R is 1. And at this point, both L and R are pointing to the same element, which is the minimum element that we have. And then we can check if nums L, the first condition that we have, returns true. So essentially this case works. We don't run into an indefinite loop like as we checked. So probably we can also submit it with this. I think it should work. Same thing. But I just wanted to do a dry run and also to show you how you can test your code. And if during an interview, if you have to showcase how the dry run works, you have to write it like this and explain line by line that initially L is 0, R is 2. We first check the if condition. If condition doesn't return true, then compute the middle element. So you have to explain all the steps. Does that make sense? Okay. Now we go to the advanced problems for these two questions. So the first question that we want to do is searching in the sort. Yeah. So this is the first problem that we want to do. Let me um so please go through this problem. This is exactly the same question that we did just now before to this, where we are searching in a sorted and rotated array. But only difference is that here the elements can be repeated, and that's a big issue. I'll explain you why. So elements can repeat, and it's not necessary that the elements are going to be unique. And we need to find in this um in this array a given element. Uh, Before solving this question, I would like to first hear what all corner cases can you think in this question, because I think solution comes at a later stage. First, I would want to see like if you guys are able to think around the corner cases that that can potentially happen in this, because that is very very important to first analyze the corner cases in this problem. This problem and the next problem are similar, and both are almost, you can say, medium to hard questions. Yeah. Hmm. True. So as you said, totally can be there. So if this is the array that we have, this is a sorted and rotated array. This is one case where left end, so the edge case one that we talked about, is both left and right values are same, correct? Can there be a, but in this case, if we take a look at this example, so if we find the middle element, what is the middle? I think this is going to be the middle, right? So maybe you can just write the marker 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 0 plus 9 by 2 is what? 4, right? So 7 is the middle. But here the middle element is different. So even if we, let's say we search, if we compare 7 with the right, we know that this is like a unsorted range. right? We will still be able to find out which part is the unsorted, which part is the sorted. That's what our initial analysis is, right? We want to first check which range is the sorted range. So even in this kind of part in this kind of scenario, we will be able to say that yeah, this is a sorted range, the left hand side is a sorted range, and then we can check if the target is in between these two markers, then we can switch to this part. Otherwise we can simply switch to the second half, which is this. So that's still like a simple one. Even if both left and right are same, we can still do that. Can you guys think of more corner cases? There are more you can say difficult edge cases in this problem. Hmm. Very good. What if all the elements are same? Excellent. So let's say what if all the elements are same? I give you an array 3 3 3 3 3 3 3 and ask you to find 4. Let's say find 4. This is a valid scenario, right? Here all the elements are repeating and it's a non-decreasing order. Non-decreasing order, as I mentioned, it means that it's the elements are not decreasing. It's a non-decreasing order, and they are duplicate. This is one scenario. What if I give you another scenario like this? Let's say that 4 actually exists, but here the 4 does not exist, right? But let me modify this to a scenario where 4 actually exists somewhere in the middle, somewhere. I don't know where. Now, how will you handle it? How will you find whether this is this a valid scenario? 3, 4. Let me think about it. Yes, this is a valid input. This is a rotated array. So the actual array was, I mean, the actual array was like this: 3 3 3 3 3 3 3, and last में 4 था. So at the end there was a 4, and then you have rotated it from here. Like all these elements, you have sent it to the front. So in the last you have just two threes, and then in the front you have this sequence in the front, which is illustrated in line number 10. So here you need to find 10, for example, find 4. Now, in this kind of situation, the problem that you will face is that when you compute your middle element, your left element, and your right element all are going to point to the same 3. So L is 0. Let's say L is here, R is here. Okay, where is M? M will be somewhere here, right? Let's say M is here. Now both are pointing to 3. How will you find out, like how will you determine where do you have to go? Whether you have to go to the left half or the right half, how would you find out? Is everyone getting the edge cases here in this problem? The main challenge over here is to handle these scenarios, and trust me, when this question will be given to you, interviewer will be very interested in discussing the edge cases first before attempting to even write the code. Or even if you wrote the code but you're not able to come up with these cases, it will be a huge negative. It means like you have not really accounted for these scenarios to happen. So first aspect is to think around these corner cases that can happen in this question. And now the second scenario is like, how do we handle it? That's the second point. So we'll now discuss how do we handle it. But first step was to first find out. So this is the major corner case that we have, in which L and M and R are both pointing to the same element. If L and M and R are both same, all are same, then it especially means that this actually means that we cannot apply the binary search. Here we cannot do the binary search in this kind of situation. So what do we want to do is we want to trim down our array. We we can first compare the middle element with the element that we are finding. If it is not the same, we know that on the left hand side we have the same element, on the right hand side we have the same element. One approach is you can just reduce your R, move to one step back, and then do the same comparison. Then you can do the same comparison between this 3 and this 3, and then you can hope to find that you can hope that you will see a different value of M. So instead of seeing this value of m, you will see a different value of m. But let's say unfortunately you again see the same value of m. Then again what you can do is you can again move your right one step back. The reason you're ignoring this element is because this element is already existing in L, it is already existing in M. So it means even if you lose out on this element 3, it is not going to cause you any issues, right? Even if, let's say, m was not, I'm just saying, even if m was not pointing to this and you had to find out this 3 element number 3, your logic will still be able to somehow find this using the binary search, because you still haven't lost all the occurrences of 3, even if you are moving your right pointer one step back. So this is like one possible way you can do. The second possible way you can do is you can in fact move both your left, in case if your L, M and R all are same. Let's say L, M and R all are pointing to the same thing. In fact, you can just move both L and both M one step forward. So you can move R one step back and L one step forward. So you can just simply ignore these two numbers. So you can cut off the additionals 3 and 3 which you are noticing here. Now you again apply your binary search, you find a new M. So let's say in this case, our R had moved to this, the second last index, M and L had moved to the first index. Then we again find the middle element. What is the middle element here? I think the middle element doesn't change. It still points to 3. Since it still points to 3, we are still unable to decide where to go. So we can simply again reduce them one step back. So R can move to here and L can move to again one step here. So it becomes kind of this. Now, now notice that now R is pointing to a different value 4. So now when we find middle, we can actually we can actually find a sorted array. Now we have a way to check which part of the arrays are sorted and which part of the array is not sorted. And now we can easily like proceed from here. Does that does that make sense? Okay. Awesome. So this is the approach that we are going to do, and we can tweak this approach in both the ways. As I said, either you can move just your R, let's say if this kind of scenario happens, still it is going to work, or if you, or you can move your L and R both at the same point if let's say your L, M and R are same. Also, one important thing to note down in this approach is the time complexity that we have in the worst case is not log of n, it is going to be big of n in the worst case. Worst case happens if you have all the elements as same in the given array, let's say all threes, and you have to find four. So you have to like basically in every single iteration you have to you can move L and R one step forward and back, but then you're not reducing the size by half. You're just reducing the size by 2, by -2, right? Or by -1 if you just choose to move R. So you have to iterate over all the elements in that case, even in even in the binary search approach. But yeah, for the other cases, if it's, let's say if it's not this kind of array which is given to us, uh, so the time complexity can be log of n, depending upon the input type. If it's not all repeated elements, I mean, it again depends upon, let's say there's a million elements in the array and only two elements are there, and only two, let's say one and two are there, and the array is filled with just ones and twos. Again, it is going to fall into a big of n kind of worst case, right? Because only for one scenario you will be able to do a binary search, and then you will again fall into a linear search. So you can say that it depends upon the type of the array that we have. If there's a repeated elements and a large number of repeated elements, then there will be a uh, the number of linear operations that we would end up doing will be quite a bit. But if it is a properly, let's say the repetition is uh, is not the number of repeated elements are not as much as the number of unique elements that we have in the array, then in that case, yes, we can say it the algorithm is going to run in a log of n time as the so this can be our amortized time complexity in case if we are let's say looking at a huge data set which has a mixed number of unique elements, some are repeated, some are unique. So in that case we can say that, but I believe you should be able to explain in which case it should be big of n. That is going to be our worst case. Log of n only if uh, let's say a significant number of elements in the array are the unique elements and we have like less repetitions uh, in the array. Does that make sense? Okay. S- So now we are going to um, we are going to implement this approach. Um, okay, so let's start with this approach that we decided. So L is equal to 0. R, let me switch to a shorter view. Okay, so R is going to be length of nums minus 1, while L is less than equal to R, the same. So I just don't need to put the bracket. Okay, fine. So while L is less than equal to R, then first we find out the middle, L plus R minus L divided by 2. Then I'm gonna check in case if the middle element is my target, then just simply return that. So do we need to return the index? We need to return a boolean, okay? So if nums of m is equal to target, then return true. That's the very first thing that we do. So it means that we have found the target and this is what we wanted. So just simply return true. Now we are going to check for this interesting case if we are unable to decide which part we have to go, whether we have to go to the left or we have to go to the right. So this part we are going to write specifically. So if nums of L is equal to nums of M and nums of M is equal to nums of R. So essentially all the both L, M, R are same. In that case, we are unable to make a decision, right? Where do we have to go? And that's a very tricky case that we have. So in that case we want to skip we want to trim the array, we want to trim the searchable length by both the ends from the left side and the right side. uh, so and why and let's say if somebody asks you that hey, you are trimming the length from both left and right, what if that element itself was the let's say was a target? That cannot be there, because if that was a target, then it was equal to m, it was equal to nums of m as well. And if it was nums of m, we would have already returned true for that. And again, we are not losing this value because we have the similar value in the m. So even if we lose out on the values of l and r, we still gonna hold that value in m. Does that make sense? Okay, so uh, L plus equal to 1 and R minus equal to 1. This is the very first step. Now I'm gonna check in case. So if this was the case, I just wanna do this and then skip this entire iteration. So you can also just write continue here if you want. So I don't wanna like process anything further, or you can just write a elif and whatever seems favorable to you. So I'm just gonna write elif over here. So I'm going to check if my, let's say the first half is sorted or the second half is sorted. So let's say if I'm checking my first half is sorted, so nums of m is greater than equal to nums of l. If this is the case, then we know that my first half is the sorted half that we have, if this is the case. So in this particular case, if my first half is sorted, now what we're gonna do is, please note down that this case cannot happen. This will only happen if the first half is actually sorted. If the first half was unsorted and the middle was repeating, then it will always be equal to to the rightmost element as well. Uh, so if somebody is thinking, let's say, what if my left half is not sorted, but this condition is still true. It means that middle element is same as the left element, but then in between left and middle, we have a minimum element somewhere. That cannot happen. That cannot happen, because if that were to happen, then your right element should also be equal to the middle element. You can try to picture this scenario, but let me know if somebody has confusion in that. I can give some specific examples and explain why this case can never happen. This case will only happen if it is strictly sorted. So if left is sorted, again left is sorted doesn't mean that the elements cannot be repeating. Elements can repeat, but the pivot is not within the left part of the range. That's what I'm trying to say here. Left is sorted, or pivot is not in left array. So if this is the case, it means my left is the sorted one. Now I can just easily check if my target is within this left part. If it is yes, then I'm gonna switch to this left part of the range. Otherwise, I'm gonna switch to the right part of the range. So here, if target is less than is greater than equal to nums of L, and target is less than nums of M. If this is the case, it means the target also exists in the left side of the range, which is the sorted range that I have. So I can just switch to R is equal to M minus 1 simply. Otherwise, it means that the target will be there in the other part of the range, which is L is equal to M plus 1. Uh, and then the last part will come else, which will mean that the right part is the sorted. So instead of the left being sorted, the right is the sorted. And again, we can give it a check over here. If right is greater than nums of m, and if target is greater than nums of m and target is lesser than or equal to nums of r, then it means it is actually there in that. So I can just shift to L is equal to m plus 1, else R is equal to M minus 1. And then finally, if the target was to be found, then we would have returned true. But if the target does not exist, then in that case, we will simply return false after all the loops are done. So return false. Does it make sense? Let me switch to the bigger view and pause here for a bit. Is everyone uh, is everyone able to understand what we did here? If yes, please give a thumbs up or say it out. Everything clear, like all the edge cases cleared. And why is this code able to handle all the edge cases? This part is able to handle all the edge cases that we have. We are trimming down the array in case if both the ends are same, and even if the middle is same, it means that we cannot make a decision whether to go to the left or whether to go to the right. So since we are unable to make the decision, um, and we have to trim the left and the right parts. Okay. Let's run it. Let's run it once and see if it's passing. Nums is not defined. It is, okay, that's one error. What else? That's it. Okay, so this passes. Let's submit it. Okay, so this passes. Let's attempt another problem. We have a bit of time. So the next problem that I wanted to attempt was finding the minimum in the uh Where was it? Finding the minimum in the sorted array 2. Finding the minimum in the sorted array 2. Okay, here it is. Let me first copy this question. Let me just copy this in the doc. Uh, just for the so this problem, this question is this, and minimum is sorted array 2. Give me a second. Finding the sorted array 2. Search in the sorted array. Yep. Okay, all right. So we have put this question over here in the doc. Heading to cool. Let's start with the next problem, which is going to be finding the minimum in the sorted array. Uh, part two. Um, okay. This is an interesting question, as we can see. Uh, can you guys think about it based on the similar logic that we have done just now? Do you think it's possible to use the similar kind of logic here and like able to come up with a solution? Here we need to find the minimum element, but the array can have duplicate elements. The only difference with respect to, so array can have duplicate elements and we need to find the minimum. Thoughts, questions? Alex, Mitasha, Palak. Hmm, okay. Do we need to change anything in that logic that we were using? So basically, maybe do we remember the code that we had wrote for this minimum, finding the minimum in the sorted array? Can you help recall the logic that we had used to find the minimum? What was the logic we were using to find the minimum? Yes. Mm-hmm. Correct. But please note that in the previous in that question, we were using left less than equal to right, uh, because the elements were not repeating, right? So here we cannot directly use that less than equal to logic. Probably we can use less than, but we should not be using equal to. That's the very first thing. Does that make sense? And how about, let's say we find a middle. So one question, if left is strictly less than right, for example, if right was 3, can this be a scenario? This is not a valid this is not a valid case, right? Which I have described here. This is not a valid case, but this can be a valid case, right? This can be a valid case. So if left is strictly less than right, if this condition ever happens, I mean, if nums of left is strictly less than right, then it means that this is the answer, right? The left is the answer, correct? In that case. Um, okay, and so this can be one scenario in which, let's say, the leftmost element is lying at the right part of the range, right? This can be one scenario. What can be the other scenario? The minimum element can be present in the middle. So one, two, three. This can be the another case, right? Um, and then it can be like this, can be like this. So in this case, we can use a similar concept, like we would we would find the middle, we will find the sorted range, which is the sorted range to look at, and we would try to look this element into the unsorted in the unsorted range. So here we will find the middle as 1. We know we compare it with the right side range. It's a sorted range, so we know that the we don't have to go to the sorted range. We have to go to the unsorted range, because that is a place where we will find the minimum element. So we go to the unsorted range, which is 441. So left starts from 0, right is at here, and middle is at 4. Then we again compare 4 and 1. We say that, oh yeah, this is like strictly decreasing. So it means this is like a unsorted range that we have. So if it's an unsorted range, I can straight away go to my unsorted range, and so I go to my unsorted range here. L and M both are same, and then like basically I found the element and I can return back. Um, so basically what I'm saying is that we can use pretty much the similar logic that we had, um, and just tweak it a little bit to make it work for this scenario as well. That's what I have in my mind. Does it make sense? Um, okay. Any other any other thoughts that you have? How can you attempt this problem? Alex? Yeah. Yeah. Mm-hmm. Uh-huh. Yes. True. So basically, we can use pretty much the similar approach here. So what we can do is we can define our L as 0, R as length of nums minus 1. Then we can have our while loop while L is less than equal to R. Um, then we can have we can first check if we can first compute mid as L plus R minus L divided by 2. Then we can check if my nums of L is same as nums of mid, and nums of mid is same as nums of uh, nums of R basically. Then I can just simply increment cliff of uh, the additional ones, right? We can simply cliff off that. But in this case, I just have one small thing. So if we have just a single element inside the given array, so the problem was that in the first case, we were comparing the middle element with the given target, and if it was there, then that's the answer. But imagine that if the array is given as one, just single element, it can be two as well. In this case, our L and R both will be 0, 0. M will also be 0. And then this condition will also come true. Then we will happen to increment and decrement L and R both, and both will, like, L will become 1, R will become minus 1, and then this while loop will simply exit. So do you are you able to get that? Uh, this part would be a little bit of problematic here. If so basically trimming of both L and R is not like a is not seemingly a very good idea in this case if we trim off both L and R at the same time, because that can happen that that may be the only element in the array, and if we trim off both of it, then we basically and it can also happen, let's say we have two for example. So L is pointing to 0, R is pointing to 1, and then you find the middle, which is L itself, and again the condition satisfied. So L will reach to 1, R will reach to 0, and then what? Like you will end up um, basically at the end you will be like you will come out of this while loop. So for this is still okay, because let's say we can return the nums of R or the nums of L as per the logic, but for the one element case this can be disastrous if we do this. Like, is that understood? What are we trying to avoid here? Does everyone understand this? Why we cannot just simply blindly uh, trim the left and the right directly? That can be one corner case we might miss. S- Yes, that's a good question. So why it was not a let me go back to the previous question. The reason there was we were actually searching for a given target in the rotated and sorted array, if you remember. So if we are searching for it, you have a given target. So the first step we were doing after computing the middle was we were comparing if target is equal to nums of mid. This is what we were doing. And if it was there, then we were just simply returning it back. So it was not a problem, because if that was the only element and that was same as target, then yeah, we will just simply return it. But in this case, it is a problem. So what if we maybe handle it at the end? So just comment it for a bit. Let's first write all the important pieces that we have. The first important piece is we are trying to look for a strictly unsorted portion, and then we want to switch to that, correct? And also we are looking for a strict okay, the concept is that we are gonna use the concept that we had done in the first part of this problem. If nums of L is strictly lesser than nums of R, for example, then we know that we have found the answer. We can just simply return R, uh, whatever is the L. So we need to return the number, or we need to return the number. So we can simply return nums of L. This is the very first thing. So if L is smaller than R, it means this is the minimum or the most minimum element that we have. If it is strictly less than R, that's a very first thing. Then we can check in case if the right portion is strictly unsorted one, or the left portion is strictly unsorted one. So if nums of mid, let's say the right portion is unsorted. If nums of mid is strictly greater than the nums of R, so it means that the right portion is the unsorted part. Right portion is unsorted, strictly unsorted, okay? So if right portion is strictly unsorted, it means that the minimum element is going to be present in the unsorted portion. This we had talked about in the first version as well. So in this case, we are going to switch to our the left pointer to m plus 1. Elif, in case if the left portion is the strictly unsorted, so nums of mid is less than nums of left. So here I'm only doing the best case scenarios. So if this is strictly uh, if this is strictly greater than nums of r, it means the right portion is we can totally with confidence we can say that the right portion is unsorted. In case if left portion is completely unsorted, so left portion is unsorted, then we know that the minimum element that we are searching for exists into the right side. So we can just switch to r is equal to mid. That's the that's a very second thing. And now comes the last condition, which is our else condition, which doesn't fall into any bucket. So what it essentially means is that the left portion, neither the right portion is um, uh, strictly unsorted, nor the left portion is strictly unsorted. So what it means is that we are kind of sitting in a scenario in which the middle, like the minimum element would exist somewhere, but it is not, but neither of the portions is strictly unsorted. It means that the middle element is um the middle element that we have, I think, is same as both L and R. That's what it means. So if middle element that we are having is same as nums of R, and the middle element that we are having is same as nums of L, does it make sense? What does the last else condition means? So in fact, we could write that specifically also in a first if condition. We'll do that. We'll do that tweak later on. But here we discuss this fact that we cannot decrement and increment left and right at the same time. Like we should not be doing that. Because for a single length array, that is going to cause problems. So for this, either we can increment L or we can decrement R. We can do any one of them at this point. So what I'm going to do is I'm going to decrement R at this point. I'm not going to do both. So I'm just going to be decrementing R over here. So we just say that, okay, just move back your right pointer by one. We can confidently say that the right most element that we have is not the least element. And even if it is the least element, there are other occurrences of that least element inside my array that will be able to find in the rest of the other iterations. That's why we are able to do R minus equal to one here. If anyone has any doubts in this, please let me know. And the idea is, since we are decrementing our the pointer R one step back, so at the end we will end up uh, the least negative element that we will be ending up is going to point to, let's take an example. Since we are decrementing mm, R by one, so let's say we were having this scenario where there was a single element um, inside the given array, which is 2. So L is 0, R is 0, M is 0. Okay. So the first condition is not true that we have over here. The second condition is not true. The third condition is not true. So then we decrement the value of R by 1, and it becomes R becomes like -1, and um, we come out of this the while loop that we have. And at this point of time um hmm, at this point of time we can simply return nums of L over here. I'm just also trying to see if this is what we should be returning here. So probably if we try to run it for one scenario, L is equal to mid plus 1. Okay, this works for these two scenarios. Mm, let's try to submit it and see. Okay, so essentially what we are doing is we are uh, like uh, we are trimming the edges, but we are not trimming both the edges. We are just trimming one edge. And since finally what is going to happen is either it will be, since here we are returning nums of L, right? So we are saying that if it is strictly lesser than nums of R, it means that nums of L is the answer. So essentially what after doing this iteration, what we are trying to achieve is we are trying to achieve the sub portion of the array or the element in such a way that L is going to point to the minimum element, the least element inside this given array. That is the logic that we are trying to do. In fact, if you wanna use the previous approach, we can do the previous approach. We can just say that if nums of L is same as nums of M, nums of mid, and nums of mid is equal to nums of R, then just do a R minus, just do a R minus minus, and you can remove this uh, last line. So this case will only happen if it is not a strictly and the rest of the cases will get covered with this. But this has to happen as a part of else if part. So this will be like all under elif, like all under big elif. So this can be, you can also try to see this will also work. Hmm, expect a semicolon. Okay, so this also works because the approach is pretty much the same as we are. Yep. So the logic is pretty much the same. We have just converted it to the same logic that we were having. So essentially we are checking if both the ends are same and if they are same as the middle, we are trimming the edges. But please note that we cannot trim both the edges. Otherwise um, we might over exceed the ranges, and then we might skip past this element, and because there is no way to compare the element over here. In fact, in the previous question also, you can just to unify the template, you can just do a r minus minus in that question as well. You don't have to say l plus plus even in that question, and still that is going to work. So I can show that to you, so that the template can become the same, and you can use the same template in both the questions. So if I first, let me just copy this. First of all, is this clear to everyone what we are doing here? We are using the similar logic and we are solving it in the same way. Yeah. Okay. So let's say if all the, we can do that. So let's say all the elements are same. Maybe take the element as 4. So 5 is the length of the array that we have. Okay. Now in this array, if we take this example on this, so initially what is going to happen is L is going to point here, R is going to point here, correct? Now, uh, after this, the middle element will be like this will be the middle, correct? Highlighted one. Now we check whether L is equal to M and M is equal to R, which is correct. That's the case, right? So we are every time what we are going to do is we are going to shift R. We're going to trim the length of the array by 1. So initially it shifts here, then R shifts here, then further it will shift here, and then further it will shift here. It will come to 0, and then further it will shift. R will finally become -1 and L will still remain 0. R will become -1, and that's the point where we stop this iteration, because we have a logic here. While L is less than equal to R, keep doing that. We'll stop this iteration over there, and then finally we will be returning whatever is there with the L, because that's our lowest value. We are capturing it in this way, and in fact that's the condition we are having in line number 9. If nums of L is less than nums of R, then we are returning nums of L. So using the same principle, that's why I'm returning over here nums of L, because if they are duplicate values, I'm not trimming. Let's say if I were to move L plus equal to 1, then I would be returning R in that case. Instead of returning nums of L, I would return R. Does it make sense? Here we are trimming the array if it's a duplicate, but we are trimming only one side. We are not trimming both the sides. Yeah. Uh, this particular, I don't think if in this example it might come across. Um, okay. Let's say this is the array. Simple as this. So L and R both it's a one element array. Okay. So even for one element it won't work now. So don't you think that if it's not working for one edge case, you should not, it might not work for other edge cases also, but if we have found an edge case for which it doesn't work, then we should not be trimming both the sides. It's clear that if it doesn't work, I mean, there can be other examples also, but if it doesn't work for one example, then it cannot work for other examples as well. It, so in fact, you can, I think for other examples, it will work just to tell because if you have more than one element in an array, then you will ultimately end up pointing to the minimum element. Let's say there are just two elements in the array, like four elements, but one is two unique elements and one of them is like a minimum. Okay. Then you will end up pointing to the minimum element in any way. And then your both the pointers will be pointing to two different elements because there are more than, um, you can say there are more than, in fact, this condition will occur here also. Imagine it this case. So L is here, R is here. Since L and R are both same, so you what you do is you trim both the sides. So L becomes here, R becomes here. Then again you say that okay, but here M is not the same, right? M is different for both. So maybe we can just extend it like this. Now your L is here, R is here, M is here. Okay. So you first trim both the sides. So it becomes L comes here, R comes here. Now you again find the middle. The middle element is again 4. So you again trim both the parts. So it comes here, it comes here. But now your middle element changes. Your middle element is actually 3, which is not same as this. So you will not trim both the sides now. Now you will be checking if you will have a middle element here. You will be first checking if your L is strictly shorter than R, which is not true. So you'll find out the unsorted range. The unsorted range is left range that you have. So you are going to look in the left range. The left range is from 4 to 3. So it means you will in line number 14, this code will execute. So R will be set to 3. So R will be set to 3. L will stay there where we are currently. Then again the loop will run and now we are going to check if L is strictly less than R, which is not true. Also the LMR case doesn't hold true because L is not same as R, so the first condition doesn't true. Then we find the unsorted range. The unsorted M will be pointing to L. 4 plus 3 by 2 is how much, like sorry, L plus R by 2 will point to L only because they're consecutive elements, right? So so in this case, so even in this case, your M will be pointing to L. So L and M are both same and R is different. So you will be checking if which part is the unsorted. You will get to know that, yeah, the right part is the unsorted part, right? So you will switch to the right part in line number 11. So this condition will, so line number 11, this condition will be true. This condition will be true. So, and then your L will move to the next step and R will stay there. So L and R both points to 3 basically after this. Okay. L and R both comes to 3. And now we again check this part like whether uh, mid is this. Okay. So as you can see in this case, this will again hurt you. So now we have gotten to this part. Here L, M are both same. It's the same element. Now we check if they three are equal. The three are equal in this case, right? Because all are pointing to 3. So if we are trimming both the edges, then we will end up moving L to one step forward and R to one step back. So L will start pointing to 4 and R will start pointing to like 4, the below one. Does that make sense? And then the code will exit, but the answer will be wrong. So L and R are both pointing to 4, but ideally the answer is 3. Does it make sense? So that's why we should not be trimming here both the edges. In fact, just to make the things uniform, that's what I'm saying. Even in the previous question that we did, so that you don't have to remember two different solutions. So let me just go back to the previous question, search in a sorted rotated array. Let me share this. Uh, Even in this question that we did, instead of trimming to both the sides, what we can do is we can trim just the one side and still it should work. Just to show you, it still works. Okay, so you can, like, you can just forget about trimming both the edges. You can say that I'm just gonna trim from one side, I'm gonna make it a little shorter and see if it's still if the binary search I can apply or not. So you can just apply the same template in both the questions, and remember just one approach. Okay, any questions in this? I Is this understood? Rest of the folks, it's a little yeah, it's a little tricky question. It's not it's not straightforward, and it's categorized as hard as well. But yeah, once you understand the logic, it doesn't seem as hard. So please give it a try at your end. And has everyone tried it on their own IDs, this problem? Sure, I'll share with you the sheet. It's there in the sheet, but I'll share with you. So yeah, this was the. I have one more problem, but I think we are pretty much over time, and I have a meeting as well. So the last question that I wanted to discuss was this. Uh, this is a log question here on GFG on Leetcode, so we need to find this question somewhere else, like GFG. So maybe let me maximum number of buckets that can be filled. I think that's a different question. This is the question: pour water between buckets to make the. We'll discuss this problem in the next session. So pour water between buckets to make equal. We can solve it on Algo Monster. I think this will provide us a platform to solve. So we'll discuss it in the next session. Okay. This is the remaining question on this. All right, guys. Thanks for joining, and let me know if you have any doubts. Post it on the group or DM me personally. Tomorrow we should be meeting for the system design session, and we will be doing the Redis design. That's what we were discussing in the previous session. So we'll be continuing with that. All right.